Okay, so we have two quotes of the day today. Apparently, I forgot to write out what we're planning today, but today we're planning on doing the rest of factoring special products, and then after that, moving into 7.6 quadratic equations. So that's the plan for today. We do have spring break next week, so enjoy the break. I do strongly recommend, though, because there's such a quick turnaround when we get back between the break and final exam week, there's about maybe 2 instructional weeks or so when we come back, and then we're already in final exams. It can be really difficult to get the momentum back up, really in any course, but especially in a math course that builds so strongly every topic on every other topic. It can be really tough to get that momentum back up if you take a week or what amounts to really a week and a half from Thursday to 2 Tuesdays from then, completely away from the material. So I do recommend kind of checking in a couple of times over spring break with the material. So in this class and other classes. So even if you just took a half of a day on Tuesday and maybe half a day on Saturday and reviewed a little bit of each of your classes, reviewing a little bit of the maybe this week's work or something like that. And then maybe on Saturday, kind of reading ahead a little bit, just kind of touching in with the material a couple of times throughout the break. You can still have a super nice break, still can be super relaxing, but putting in a little bit of work like that will kind of help keep the momentum up, so to speak. And then, once you're through finals week, then you're into summer, and then you're kind of free and clear. You can kind of, forget everything and just uh, just focus on relaxing at that point. But so have a relaxing spring break, but probably best practice to check in a little bit with the material a couple of times. Okay, my window's a little wonky here. There we go. Two quotes of the day today. I think these are kind of related to each other, which is why I put them together. One is from US chess grandmaster Maurice Ashley, where he's talking about chess, and he says there are three types of trades: forced, fantastic, and foolish. If it's not forced or fantastic, then it's foolish. And Warren Buffett, who says there are no called strikes on Wall Street. So making a baseball analogy about calling strikes. So what's the lesson here? Well, if you're not familiar with chess, um, so what is a trade? That's where maybe like, I use my knight to take your bishop, and then you take my knight back. So now I traded my knight for your bishop effectively. Uh, so what's different about a trade than a normal move? Well, if I move my knight to this square where it's not attacked, and I don't like that move, next move I can move it back to the previous square. I can kind of undo that. But if I take your bishop and you take my knight, I can't undo that trade. I can't get my knight back. I mean, I guess I could, get a pawn to the end of the board and turn it into a knight, but effectively I can't undo that, right? So that's the difference here, is that a trade fundamentally alters the structure of the game. It's more permanent. And similarly, Warren Buffett's quote, there are no call strikes on Wall Street. Well, so a called strike is a baseball term where if you get a pitch given to you that's good enough and you watch it go by, that's a called strike if you don't swing at it. So if you knew that ahead of time, you might as well swing and try to hit it, because it's going to be a strike if you swing and miss, or it's going to be a strike if you stand there and don't do anything. But you don't know that ahead of time. So Warren Buffett's statement, there are no call strikes on Wall Street, what's he saying here? He's basically saying that when he is thinking about going into an investment, that's a pretty substantial decision. And he'd much rather, if he has any, questions about that investment, isn't really sure about it, he'd much rather sit on the sidelines and wait for the next really good opportunity to come down the line, right? Wait for that, fastball pitch that's right down the middle, not one that, might be good or might not be good, right? There are no call strikes in Wall Street. So I think both of them are saying something like, uh, take care when making decisions, but take a lot more care when making decisions that are more permanent, right? If Warren Buffett throws a bunch of money into a company, he's not really easily able to get out of that position. And I think this goes for life as well. There's another kind of quote that I've heard. It goes something like, there are three types of decisions in life. There are hats, haircuts, and tattoos. A hat, if you put on a hat and it looks silly on you. Your friend, points out, says that hat looks silly on you. Well, you just take it off. If you get a haircut that looks silly on you, well, it might last a couple weeks, but it's going to grow out pretty quickly, and you can get it cut again. But if you get a tattoo, that's quite a bit more permanent. So when you're thinking of decisions that will fundamentally alter something more permanently in your life, take a lot of care to make those decisions with a very high quality. And kind of conversely, um, try not to expend all of your cognitive energy on the little minutia that don't really matter so much, right? Um, so leave yourself some margin for making those big important decisions, right? So things like, what job are you going to accept? What career field are you going to go into? If you have a good job opportunity, but it's in another state where you won't be as close to family, or a slightly less optimal, let's say, job opportunity, but it's close by, like making decisions like that are much harder to undo than, some of the decisions that bombard us every day and that feel more urgent, but maybe are less substantive. Okay, so moving on to factoring, 7-4 factoring special products. And the one we looked at last time was perfect squares. And let's just do one more example, one more exercise in perfect squares, and then move on. So we said that the pattern that we were looking for was that we had two terms that were perfect squares themselves. And if that's the case, then it's possible that the polynomial we're looking at is a perfect square, but not guaranteed. We then have to check the middle term. If the middle term also matches up nicely, then it's a perfect square and we can factor it easily. So let's take a look at 25r squared minus 60rs plus 36s squared. And I noticed that 25r squared, well, 25 is a perfect square. It's 5 squared. And then we have 5r squared. And similarly with 36s squared, 6 squared is 36. And then we have 6s squared. So this is a candidate for a perfect square trinomial. So here A would have to be 5r. Let me write that a little better. And B would have to be 6s. So then my question is, what is 2ab? I don't know why I can't write 5 this morning. So 2 times 5r times 6s, or that is 60rs, and that is exactly what we have in our middle term. And we see this factors as 5r and 6s squared. And then the sign on our middle term, this minus sign, is what connects these two. So I have 5r minus 6s all squared. The minus from the middle term is what determines that minus sign between 5r and 6s. Okay, so take maybe a minute and a half or so to do this one. Shouldn't take long, take maybe 90 seconds and go through the process. I mean, you probably know that it's going to end up being a perfect square trinomial, but go through the full process. Make sure that you get your A and B, figure out what they are, check everything carefully, all of that. So take about 90 seconds. We'll come back and discuss. Okay, so this one was a little bit tricky and was intended to serve a bit as a cautionary example that here we have 10r squared and s squared for our first and last terms. But if I look at 2ab, what do I get? I get 2 times 10r times s, or that's 20rs. But this middle term here is actually 25rs. So I actually can't factor this as a perfect square. Now, that's not to say that this doesn't factor at all. This could factor a different way, but it doesn't factor as a perfect square. But let's look at, well, what if this was 20rs here instead of 25rs? So if I change that, trying to highlight it here so you can see that I changed it, but my OneNote is not cooperating. There we go. So if I change this bit, if it had been 20rs instead, then how would we proceed? Well, then we would proceed and we would say, well, I have A and B, or 10r and s. I have a minus sign in front of my middle term, so that puts a minus there, and squared. So we do actually have to be careful to check our middle term, our cross term, and make sure that everything lines up properly. You can actually see that for this to be a perfect square, there's really only 2 choices for the middle term given an a and a b. It can either be 2ab or minus 2ab. Any other choice for that middle or cross term, and it's not going to quite fit the perfect square pattern. So, so recognizing the first and third terms are perfect squares is really only enough to make it a candidate for a perfect square trinomial. And then we do have to check that other term as well. Okay, so perfect square trinomials are kind of nice. They come up occasionally, but but I think difference of squares comes up more often, and is probably a more important one to know. I suppose in some sense they're all important to know, but you know, I think difference of squares is a bit more important. So let's look at a few examples. We see the difference of squares pattern is this a plus b times a minus b equals a squared minus b squared. So if I see that I have a binomial, if I have 2 terms where both of the terms are squared, and importantly, they have to be subtracted. If I have a squared plus b squared, this is going to be prime. I mean, maybe there's a GCD, a greatest common, or GCF, a greatest common factor that can be factored out or something like that. Um, but as far as factoring it and making it no longer a quadratic, um, it's going to be prime in that sense. We're not going to be able to factor it to the product of 2 linear binomials. So here, if I have a plus instead of a minus, essentially this doesn't work at all. It has to be a minus between the 2. But I do see that I have 169y squared is 13y all squared minus, and then 1 can be a tricky one because it doesn't kind of feel like a perfect square. We're used to numbers like 4 or 16, but 1, of course, is 1 squared, so it's also a perfect square. So a is 13y and b is 1. And here I do have a difference of squares. There's nothing else I need to check. This factors into 13y minus 1 times 13y plus 1. Okay, if I look at my next example, 49x squared minus 81y squared. I noticed that 49x squared is 7x all squared minus, and then 81y squared is 9y all squared. So again, I have a difference of two squares. A is 7x, B is 9y. And this factors as a minus b, 7x minus 9y, times a plus b. One thing to take note of here is the order of a and b matters in the parentheses with the minus. So 7x minus 9y is not the same as 9y minus 7x. So it does matter which one of these is before the minus sign and which one is after the minus sign. They have to be consistent between the original quadratic and the factored form. Okay, and this one can be a little tricky. So sometimes we see problems like this, and I look at this and I say, well, 98, that's not a perfect square. 72 is not a perfect square. And for that matter, r cubed and r are not perfect squares either. So it seems like this is not a perfect square binomial, or sorry, difference of two squares binomial. And I might be tempted to even think that this maybe is prime. Remember, kind of step zero in a sense that we had discussed in the last section is it's probably a good idea to always look for a greatest common factor first. Is there something I can factor out of the whole problem before I even start inspecting the trinomial or binomial to see if it factors again? Well, let's check. Well, I know that each term has, so I'm going to look for a common factor. I'm just going to look for something to factor out. I'm not going to right away worry about finding the greatest common factor. I'll do this as an iterative process. I noticed that each term has one factor of r. So there's one factor of r, of course, in the r cubed, and also in the r to the first. And 98 and 72, well, those are both even numbers. So I know they both have a factor of 2 in them. I know I can factor a 2r out. Maybe there's more that I could factor out. I could go through the whole greatest common factor process and find the absolute most that I could factor out. But I think in practice, a lot of times it works best to just do this iteratively like this. So I could write this as 2r times. Now, what do I need to multiply 2r by to get 98r cubed? Well, I think this is going to be 49r squared. 2 times 49 gives me 98. 2 times 50 gives me 100, right? And then I just need to take 2 off of that, or I need to take 1 off of the 50. And then r times r squared, r cubed. Minus, and then 2 times 36 is 72. And I factored out the r. So there I am. There are no more factors of r that are common to both terms that can be factored out. And if I look at my numbers, my numerical bits, my coefficients, 49 is 7 squared and 36 is 6 squared, no common factors between those two. But in fact, I just saw that this is actually 7r all squared, and this is 6 squared. And they are attached with a minus. So the bit inside of the black parentheses can be factored as a difference of two squares. I still have this 2r bit in front, and then I have a 7r minus 6 times 7r plus 6. So this bit led to this, and my 2r just came down. So my 49r squared minus 36, once I factor out that common factor, or in this case, we found the greatest common factor right away, I recognized it as a difference of two squares, and I could factor further. Okay, let's take a look at these three exercises, as well as a challenge exercise down here. So if you finish up the 3 exercises in time, take a look at this one, x to the fourth minus y to the fourth, and try to factor it completely. Factor it until all of the factors are prime factors. And this is a challenge for two different reasons. So there are two things you'll need to see here. I don't think either one of them is super difficult to see, but there are two slightly odd things you'll need to recognize in order to factor this completely. If you recognize one of them, you'll be able to factor it a bit, and then you want to recognize something else to factor it the rest of the way. Okay, so take a look at these. Let's take about 6 minutes for these three problems plus a challenge. If you don't get to the challenge, that's okay. But let's take about 6 minutes and then we'll come back and discuss. Okay, it's right about at 6 minutes. So let's review these. The first couple I think should have gone pretty smoothly and pretty quickly. We see y squared minus 9. Y squared is y squared, and 9 is 3 squared. We see it's a difference of two squares, and it factors as y minus 3 times y plus 3. So pretty straightforward one to start with. The next one, 121x squared minus 25y squared. 121 is 11 squared. So I have 11x all squared for the first term. And then 25 is 5 squared, so I have 5y all squared for the second term. And those are subtracted. So this fits the difference of squares pattern. And I see that I can factor this as 11x minus 5y times 11x plus 5y. And there's nothing more that I can do here. These are both prime polynomials. The third one, a little more challenging, 24y squared minus 54, we see that it's not immediately a difference of two squares. The y is squared, but 24 is not a perfect square, nor is 54. So I could either go through a full prime factorization here and find the greatest common factor, or I could kind of chip away at it. I do notice that both 24 and 54 are even numbers, so that means they both have a factor of 2 that can come out. So I kind of started in step 1, factoring out a factor of 2 because that's common to 24 and 54. It is a common factor. Even if it's not the greatest common factor, I can start there. So I end up with 2 times 12y squared minus 27. And now I look between 12 and 27. I see both of them have a factor of 3. I could factor a further factor of 3 out. So pulling the 3 out, I get 2 times 3, or 6. And what's left over on the inside of the parentheses, so I have 6 times 4y squared minus 9. Now I have no more common factors that can come out, but I do now recognize a difference of squares. So this is 2y all squared minus 3 squared. So this 4y squared minus 9 bit factors into 2y minus 3 times 2y plus 3. And then, of course, we have the factor of 6 in front. Don't forget about that, kind of tagging along. Now onto the challenge problem. So what makes this a challenge? Well, there are two things. The first is we have to be pretty decent with our exponent rules to remember and to recognize very quickly that, say, x to the fourth is really x squared squared. It really is itself a perfect square. It's the perfect square of x squared. And same with y to the fourth, it's y squared squared. So this really is a difference of squares where, say, a equals x squared and b equals y squared. That means I can factor it into a minus b times a plus b, or x squared minus y squared times x squared plus y squared. Now, x squared plus y squared is prime. That's the sum of two squares. There's nothing more I can do with that one. But the other thing that I have to realize to factor completely is I have to look at x squared minus y squared and recognize that it is, again, a difference of squares. So we actually got another difference of squares out of this first difference of squares calculation. And we can factor x squared minus y squared as x minus y times x plus y. So this bit here that I had outlined in green all came from the first factor, x squared minus y squared. And then the second factor in blue, x squared plus y squared, was just brought down from here. And this is something that even my calculus students, when problems like this come up, a lot of times they'll get to here, but then they don't actually bring it home and do the last difference of squares factorization. So this is something to just, you always want to check at the very end. And sometimes I don't explicitly, point it out, but you always want to check at the very end and ask yourself, is there anything that can be factored any further? So we want to really think of this as an iterative process. We want to get, our polynomial, whatever it is, into a slightly more factored form, and then work from there and get a slightly more factored form and a more factored form until we get to a prime factorization, right? That's kind of the way that if I wanted to do, say, a prime factorization of the number 24, I might think, okay, I'm not going to necessarily jump immediately to a prime factorization, but I can find a way to break 24 into two multiples. I have 6 times 4. 6 I can break into 2 times 3, or I can break into 2 times 2. So in this iterative method, I eventually make my way down to a prime factorization. We're really doing the same thing with these polynomials. Now, sometimes I start with a number like, you know, uh, I don't know, 15, and I break that into 5 times 3, and I right away get to 2 primes, right? Often in these factoring problems, that happened here, that happened here. Uh, Often that happens immediately, but sometimes it doesn't, right? Here I kind of split off one factor, another factor, which I was able to combine with the first factor, and then a third step to fully factor this one. So I really ought to always think of factoring as an iterative method. Sometimes I end up fortunate and I do one step and I get the full factorization, but sometimes I need to keep going. So I always want to check after I do one step, is there anything more that I can factor? In this case, the answer was yes, I could factor this x squared minus y squared further. Okay, and then our third section here, the sum or difference of cubes. And here we have a formula where a cubed plus or minus b cubed equals a plus or minus b times a squared minus or plus ab plus b squared. What's with this symbol? This is a funny looking symbol, this minus or plus. It means the opposite sign of the plus or minus. So this is just a shorter way of writing the two formulas. So a cubed plus b cubed factors is a plus b times a squared minus, we have the opposite sign, ab plus b squared, and a cubed minus b cubed, a minus b times a squared plus ab, opposite sign. These were minuses connecting over here, so it's a plus in front of the ab, and then plus b squared. Now, I have to be honest with you, most of the time I don't remember this formula as it's written here, and I kind of try my hardest not to memorize formulas, especially when they have minus signs floating around, because it's so easy to get something off by a negative, and then everything is messed up. So what I usually remember, or what I try to remember, is that, for instance, a cubed minus b cubed, I can factor a minus b out. And a cubed plus b cubed, I can I can factor a plus b out. Then how do I find the rest of this over here? Well, I kind of work it out like a puzzle, right? A minus b times what has to make, what does this have to be to make a cubed minus b cubed? Well, I need an a times an a squared to make an a cubed. I need a negative b times a b squared to make a minus b cubed. So if I was working this out from first principles, I would be saying a cubed minus b cubed is a minus b. I need an a squared to multiply the a to make an a cubed. And I need a plus b squared to multiply the minus b to make a minus b cubed. So if I do that multiplication, I get a times a squared is a cubed. I want to keep that, but I get this annoying minus ba squared. I want to get rid of that. Minus b times b squared gives me a minus b cubed. I want to keep that. But this minus b bit gives me a minus b, or I get a times plus b squared. I get a plus ab squared, and then minus b cubed. I need to get rid of this plus ab squared. So I need to put something here in my cross term that when it multiplies a minus b is going to get rid of the rest of this here. So, okay, what could I put here? Well, it would have to have a factor of a so that I could get rid of this a squared. And it would have to have a factor of b so I could get rid of this b squared. When it multiplies the b, so when I have, say, b times ab, that gives me ab squared, but that comes with a negative. I want to undo a plus ab squared, so I need a minus ab squared. So I need a plus ab times minus b. So that'll give me minus b times ab is ab squared. That gets rid of that bit there. And then does the last bit work out right? Well, then I would have a plus a squared b, and that undoes that minus ba squared or minus a squared b. So that's usually how I think of this. So why do I choose not to memorize this? Well, it's because of these minus signs. I mean, kind of to be fair, I've taught MAT090 enough times that I kind of do just know the pattern now from teaching it so many times, um, but I didn't really consciously think, okay, this is a formula I want to memorize. Because when we have minus signs floating around, it's really easy to get one minus sign in the wrong place, or one minus is a plus or a plus is a minus, and then have your answer be wrong. So when I have little nuances and intricacies like this in formulas, I usually try to figure out a method of reconstructing that formula. So what I remember is that, for instance, a cubed minus b cubed has a factor of a minus b that factors out, and then I can figure out the second bit if I need to. And also of note that sums and differences of two cubes don't come up so frequently. Right, I'm not using this like, 5 times a day. So that's number one, the reason that I'm okay with reconstructing this whenever I need it. It takes a little bit longer, but I don't use it super frequently. And number two, the fact that I don't use it super frequently means that if I memorize the formula, if I don't use that formula for a month or something like that, it makes it more likely that I'm going to make a small error in how I remember it if I'm not using it all the time. So that's kind of my approach to this. Depending on your learning style, your thinking style, you might prefer just the rote memorization. Just be really careful about memorizing it and really aware of where your pluses and minuses go. And maybe that along with just checking very carefully at the end, distributing everything out, checking that everything works out at the end, that might work better for you. Or you might like doing it this way where you kind of remember an idea. The overall idea is that a minus b factors out of a cubed minus b cubed, and a plus b factors out of a cubed plus b cubed. If you remember that idea, and then you can kind of recreate the formula later on as needed. Okay, so let's look at a couple examples. So here we have x cubed plus 27. We see this is obviously x cubed plus, and then 27. 27 is 3 cubed. So I do have the sum of two cubes. And I know this is going to factor as x plus 3. I need an x squared plus 3 squared. I'll write it like that for the time being so that we can really see where everything is coming from. And then I need a minus 3 times x here. So this gives me a plus 3x squared. This gives me a minus 3x squared. I need those 3x squareds to go away. So that's what I'm trying to cancel out here with this minus 3x. Okay. And if I wanted to rewrite this now, I have x squared minus 3x plus 9. One little note about this. It almost feels like this should factor further. It almost feels like I should be able to take this and then factor it again. In fact, it really looks like a perfect square binomial or trinomial, perfect square quadratic. But be really careful, there's no 2ab in here. If there was a 2ab in there, it would factor again, but there's no 2 there. It turns out that this is going to be prime, provided that we factored out all greatest common factors and all of that. What's left over here is going to be prime. We're not going to be able to write this as a plus b times something, right? It's not going to be like, whatever, a minus b times a minus b or something like that. So this trinomial bit here, provided we factored out all greatest common factors, will be prime, and that's the best we can do. So this x squared minus 3x plus 9 doesn't factor any further. And if you wanted to, you could check, right? You could say, okay, 9 can factor as 1 times 9 or 3 times 3. I need the product of two numbers to be positive, the sum to be negative. That would mean they both have to be negative. So -3 and -3 makes a sum of -6. -1 plus -9 makes a sum of -10. Neither one of those matches -3. So we could, double check if we wanted to, but provided we factored out all common factors, then this will be prime. Okay, what about y cubed minus 216? Y cubed is clearly a perfect cube. What about 216? Well, let's come over here and look at 216. It's a pretty big number. Let's see how it factors. Looking at this, and aside from the fact that I'm in the sum or difference of two cubes section, I'm a little bit suspicious that this might be a difference of two cubes because, well, otherwise factoring a cubic is not something that we've really talked about very much, right? Other than maybe a bit of factoring by grouping, we've really only talked about factoring greatest common factors out or factoring quadratics, factoring polynomials where the highest power was 2. There's no common factor to factor out here. Well, I do notice, I guess, that 216 is, well, it's even, so let's just pull off a 2. 2 times 108. I might notice that if I add 1 plus 0 plus 8, I get 9. And 9, of course, is 9 times 1. So because the sum of the digits is a multiple of 9, that means 108 has to be 9 times something. 9 times 10 is 90. 9 times 11, 99. 9 times 12, 108. 9 is 3 times 3. 12 is 3 times 4. And 4 is 2 times 2. So if I look at my primes, I have 3 factors of 3 and 3 factors of 2. So it's 2 cubed times 3 cubed, or we can combine that all under one base. 2 times 3 is 6 cubed. So I didn't, have in my table of squares or cubes or whatever in my head that 216 was 6 cubed. But I saw the y cubed minus. I saw a piece of this pattern. And I asked myself, I wonder if 216 could be a perfect cube. And I come over here, I get its prime factorization, and that leads me right to it being a cube. So I have y cubed minus 6 cubed. So this is going to factor into y minus 6 times y squared plus 6 squared, and then I have plus 6y. And the 6 squared, instead of writing it that way, I can choose to write it as 36. So that's a little more simplified, and that's my factored form. Okay, in this third example, factor 2 minus 16x cubed. Now we look at this and I see the x cubed. I'm maybe thinking of difference of cubes, but the thing is that 2 is not a perfect cube, nor is 16. However, I do recognize I have a greatest common factor. I can factor a 2 out of everything. 2 times 1 minus 8x cubed. And now I do recognize that I have a difference of cubes. 1 is 1 cubed. 8x cubed is 2x all cubed. 2 cubed is 8, and then x cubed. Don't forget to bring down the common factor that we factored out. And then I have 1 minus 2x times 1 squared plus 2x all squared, or that's 4x squared. And then plus, we switch the sign. So plus 1 times 2x, or just 2x. So here I have a minus 2x plus 2x. They go away, so that seems to work well. And there's no other common factor to factor out of anything. All of my factors are prime. All of my polynomial factors are prime. And that's my final answer. Okay, let's take a look at these 3 exercises. We'll take maybe 5 minutes or so to do these 3, and we'll come back and discuss. Maybe a little less than 5 minutes. We'll see how it goes. Okay, it's just about 5 minutes, so let's take a look at these three. So x cubed minus 64. Again, you might not necessarily recognize 64 as a perfect cube, and if you don't, you could say break it down into like 8 times 8. You might recognize it as a perfect square, but each of these 8s is 2 cubed. So it's 2 cubed times 2 cubed, or 4 cubed. So we do have x cubed minus 4 cubed, and we know an x minus 4 factors out of that. We need to have an x squared here, so that x times x squared makes x cubed, and we need to have a plus 4 squared here, so that minus 4 times positive 4 squared makes minus 4 cubed. And then for our middle term, we have to have a plus 4x. We can see, for instance, that the minus 4x squared and the plus 4x squared go away. So that's our factorization. We can check really quickly, no other common factors or anything factor out of there, so we are done. For the second one, 125y cubed plus 27. Well, 125 is 5 cubed. And so 125y cubed is 5y all cubed. And then 27 is 3 cubed. So 5y cubed plus 3 cubed. 5y plus 3 should factor out of here. I need to make a 5y cubed. So I need a 5y squared to multiply against this 5y to make a 5y cubed. And I need a 3 squared to multiply against the 3 to make a 3 cubed. And then my middle term over here is a minus 3 times 5y. So that gives me, for instance, minus 3 times 5y squared plus 3 times 5y squared, and they go away. So I've got my signs correct. That's an easy way to just check if your plus and minus signs are correct. And so here I have 5y plus 3, and when I simplify out this stuff over here, 5y all squared becomes a 25y squared minus 15y plus 3 squared is 9. Okay, no other common factors that can come out. It almost looks like there's a common factor here, but we have a common factor of 5 in both of these two, but not the third one, and a common factor of 3 in the last two, but not in the 25y squared. There's no 3's in that one. So doesn't quite have a common factor that can come out. All right, and then the last one, 6x cubed plus 48y cubed. We're suspicious of a sum of two cubes here because I see the x cubed and the y cubed, but 6 isn't a perfect cube, nor is 48. However, I do notice that 6 and 48 have a common factor of 6. At the very least, I would see they have a common factor of 2, but I might notice that 48 is 6 times 8. And I can factor out a common factor of 6 to make 6 times x cubed plus 8y cubed. And now I do recognize the sum of two cubes. X cubed plus 8 is 2 cubed. So 8y cubed is 2y all cubed. And now this sum of cubes has the sum pop out, x plus 2y. And then we need to make an x cubed, so the x has to multiply an x squared to make an x cubed. I need a plus 2y cubed, so 2y has to multiply 2y squared to make a plus 2y cubed. And then my middle term has to be a minus x times 2y. And again, I can kind of think of this minus x squared times 2y plus x squared times 2y. This middle term is making those cancel out. It's also making the other two kind of on the other end cancel out as well, but I'm only picking two of them to point out each time because that's enough to check that we have the signs correct. And then we just simplify things out, minus 2xy and a plus 4y squared to get our final factored form. No other common factors or anything we can factor out, so we are done. Any questions so far? Okay, so then three last exercises. And here we have mixed exercises. So um, no information which subsection they're coming from. Could be a difference of two squares, could be some difference of cubes, could be a perfect square, or I suppose it could be none of the above. So take a look at each of these three exercises, try to determine which of the three patterns it matches and whether it fully matches that pattern. And if it does, then factor it completely and uh, and finish out the problem. So we'll take maybe about 9 minutes on this one because, first of all, the problems themselves are a bit more challenging than some of the easier ones. And second, there's the additional layer of having to figure out which pattern to go with. So we'll take about 9 minutes, then come back and discuss. Okay, we're right at about 9 minutes, so hopefully everybody was able to get through the vast majority of these three. Um, I did wait till about halfway through to kind of start giving hints because, half of the challenge of this is figuring out which pattern each of these matches best, and then, of course, carrying out the calculations after that. So I didn't want to give too much away too quickly. If I pointed out this first one was a difference of squares, 45 seconds or a minute in, that would kind of, you know, blow that a little bit. So, um, but hopefully, hopefully I gave enough time that everybody was able to pretty much work through all of these. But the first one here we see is 11x all squared minus 12 squared. So we might recognize 144 as 12 squared, a perfect square. Um, or we might have been suspicious of a difference of two squares and come over here and, done 144 is like 2 times 72, and this is 9 times 8, and so on, and work our way down to where we see we get 12 squared. So I see 11x squared minus 12 squared factors into 11x minus 12 times 11x plus 12. And again, nothing more that we can factor here, so we're done with this first one. The second one, I see that my squared terms in this case, the x squared and the y squared term, or if I didn't have a second variable, the square term and the constant term, I note that they are both perfect squares. 16x squared is 4x all squared, and 81y squared is 9y all squared. So here a would be 4x, b would be 9y. And I notice that this is a candidate for matching the perfect square pattern. And I have to ask myself, though, okay, that middle term, I haven't checked that yet. Does that middle term match? So if that middle term ends up being 2ab, where a is 4x, b is 9y, then I do have a match, and this is a perfect square. Otherwise, it's not. So I check 2ab, 2 times 4x times 9y. That does indeed give me 72xy. So it matches that middle term. This is a perfect square trinomial, and I have 4x and 9y all squared. And the sign that connects the 4x and the 9y is a minus because that middle term has a minus on it. Be a little careful there. It can be tempting because we kind of have pluses all over the place to just automatically make this a plus. But we want to be careful and make sure that we match that sign that connects the 4x and the 9y in this case inside of the perfect square to the sign on the cross term. Okay, and then our third and last problem, factor 54y cubed plus 2000. And here we might be a little suspicious of a sum of two cubes because we see the y cubed, we see the two terms, but 54 is not a perfect cube, nor is 2000. However, I noticed that I have a common factor between the two terms. A factor of 2 can come out. So let's start there. I have 2 times 27y cubed plus 1000. And 1000 I might recognize as, well, of course, the power of 10, it's 10 cubed. And 27, if I look at it a little more carefully, I see, okay, that's 3 cubed. So this is really 3y cubed plus 10 cubed. It really is the sum of 2 cubes that's left over after factoring out the 2. It can be a little bit, it's an easy bookkeeping error to make, to be working with your complicated polynomial bits and just forget to bring down this factor of 2 in front. So we do just want to make sure that we copy down that factor of 2 at the front in every line. It can be an easy copying error to make, to forget that because you're so worried about what's happening with the variables and the factoring and all that, that you forget to copy that down. But we do want to make sure that that's there in every line. And then, of course, I have the sum of 2 cubes factors into 3y plus 10. Then I need a 3y squared to make a 3y cubed. I need a 10 squared to make a 10 cubed. And then this cross term minus 3y times 10 kind of gets rid of the other vestigial stuff that would come out of the 3y squared plus 10 squared if I didn't have that cross term there. And simplifying everything gives me 2 times 3y plus 10 times 9y squared minus 30y plus 100. Any questions on any of these factoring special products, or really any factoring at all? Okay, let's move on then. Let's move into quadratic equations, section 7.6. So quadratic equations are equations where the highest degree term is degree 2, right? For instance, if I looked at x plus 1 times x plus 2 equals 0, if I were to multiply this out, I would get x squared plus 3x plus 2 equals 0. This is a quadratic equation, so this is a quadratic equation. So a quadratic equation is an equation. It's a relation between two expressions where each expression is degree 2 or lower. Okay. All right, so if I look at something like x squared plus 3x plus 2 equals 0, I might be tempted to do something like this. To do something like our linear equation solving step, where we do something like isolate the variable terms, right? Get all the variables on one side and the constant term on the other side. And I can do this. This is a legal step to do. This is allowed. This is still a correct statement. But where do I go from here? I mean, if I didn't have this pesky 3x, and I suppose if I didn't have a negative 2, but if I, like, this wouldn't be so bad. But I do have the 3x. I'm kind of stymied here. I'm not really sure what to do. So actually, the method for solving quadratic equations looks quite a bit different than the method for solving linear equations, right? Going up one single degree from first to second degree, from linear to quadratic, uh, really essentially completely changes our approach. So we don't want to treat quadratic equations like linear equations and try to do something like isolate the variable terms and then isolate the variable. That's usually not going to work. For very simple ones, it kind of works, but for realistic examples, it doesn't work. What we really want to do is leverage what we call the zero product property. The zero product property says that if A times B equals 0, then A equals 0, or B equals 0, or both. If I have two things multiplied together that give 0, then at least one of those two things has to be 0. So let's look at this quadratic equation in this form. You might notice that this is a factored form, and we're in the chapter on factoring, so this kind of makes sense, right? If I have x plus 1 times x plus 2 equals 0, then that must say that either x plus 1 equals 0 or x plus 2 equals 0. I suppose or both, but clearly both can't be 0 at the same time. These are different things. So what do I get from this? When I take my quadratic equation in this factored form and apply the zero product property, I get one linear equation and another linear equation. I get two linear equations to kind of solve in parallel or like side by side. X plus 1 equals 0, that's a linear equation. I use the standard linear equation solving steps to solve this. I isolate my variable term, I isolate my variable, simplify, check. I get x equals -1 as the solution to x plus 1 equals 0. Or x plus 2 equals 0, x equals -2. Now wait, I got two solutions for this. Does that make sense? Well, I guess so. If I plug in x equals -1, -1 plus 1 times -1 plus 2. Well, that's 0 times 1, that is 0. Or if I were to plug in x equals -2, -2 plus 1 times -2 plus 2, well, that's -1 times 0, that is 0 as well. Actually, both of these work. So quadratic equations, at least kind of canonically, have two solutions. We have a second order equation, degree equals 2, says that we expect two solutions. Now, there are some caveats. Just like in linear equations, we kind of usually expected one solution, but sometimes we'd have maybe no solutions if we had parallel line kind of idea going on, or maybe infinitely many solutions if we had an identity kind of situation. So there are exceptions to this two solutions rule. We could have one solution, we could have no solutions. I suppose we could have infinitely many solutions, although that doesn't come up as often in discussions about quadratic equations, but it could happen. But kind of our like standard expectation is that we get two solutions out of here. And kind of as a general rule, the number of solutions we expect in kind of a canonical problem and kind of a standard run-of-the-mill type of problem is that the number of solutions we get is equal to the degree of the polynomial. So if I had a cubic, if I had an x cubed floating around, I might expect 3 solutions, or possibly 2 or 1 or 0 solutions, depending on the situation. Although with a cubic, you can't get 0 solutions. That's a little more, there are some details there, but anyway. Okay, so let's take a look at quadratics of the form ax squared plus bx plus c equals 0. The goal, the strategy, is to rewrite this left-hand side as, let's say, dx plus m times ex plus n equals 0. And then solve dx plus m equals 0 or ex plus n equals 0. And this will give me two solutions. So x equals, let's say alpha, and x equals beta. I already used up all of my good letters, A, B, C, D, E, M, and X and Y are kind of trademarked, so we'll go with these two numbers. But the goal is to factor this left-hand side into the product of two things, apply my zero product property, take my quadratic equation, instead of having one complicated equation, split it into two simpler equations, two linear equations. This is kind of a standard practice in math. We take one big tough problem and we split it into maybe two simpler problems, and we split each of those into two simpler problems, and we get to where we have just a bunch of trivial problems that we can just wrap up nicely. Okay, so if I look at an example like this, x squared plus 8x plus 7, again, my inclination might be to try to put the 7 on the right-hand side as a -7, separate my variables and constants, but I know that that doesn't really work in quadratic equations. I can do that first step. It's a perfectly legal algebraic first step to subtract 7 from both sides, but there's nothing that I can really do from that point forward. So instead, I focus on factoring first. I can factor this into x plus 7 times x plus 1 equals 0. Now, my zero product property says I have the product of two things equals 0. It's very important. It's crucial that this right-hand side is 0. There's no zero product property for 2 or something, or for 12, right? Instead, I can't say that if the product of two things is 12, then one of the things is 12 or the other thing is 12. That doesn't work. So it's crucial that this right-hand side is 0, which it is here. And now I see that I either have x plus 7 equals 0, or x plus 1 equals 0. Or in other words, x equals -7, or x equals -1. And I can even check these. I can come back up here. Let's check x equals -1. Is this a true statement? Well, I have 1 minus 8 plus 7. Is that 0? Yes, that's true. I can also check x equals -7. Is it true that -7 all squared plus 8 times -7 plus 7, is that 0? Well, -7 squared is like 7 sevens, right? The negative squares off, minus 8 sevens plus 1 7. I have 7 sevens plus 1 7 is 8 sevens, minus 8 sevens. Indeed, all of that cancels and goes away, giving me 0. Or I have 49 plus 7 is 56, minus 7 eighths is 56, is 0. So both of these are solutions. If I see a problem like this, x squared plus 14x equals -13, I know that despite this kind of feeling like the good way to go, if it's phrased this way, my variables are already separated from my constant terms, but I really need a 0 on the right-hand side here. I really need to add 13 to both sides to get a 0. If I have stuff on both sides of the equation in a quadratic equation, I use my properties of addition and subtraction to move everything to one side. And typically I'll move everything to the side that gives me a positive coefficient for x squared. That just makes my life a bit easier. So now I have x squared plus 14x plus 13. I factor that into x plus 13 times x plus 1 equals 0. And then my 0 product property says either the first thing is 0 or the second thing is 0 if their product is 0. Or in other words, x is -13 or x is -1. Those are my two solutions. Or similarly, if I had a problem like this, x squared plus 100 equals -101x. Again, I want to get, I notice this is a quadratic equation. I want to get everything on one side. And then I want to factor. I'm making these easy to factor so that we're more focused on the process than doing the factorization. I apply my 0 product property, x plus 100 equals 0 or x plus 1 equals 0. X equals -100 or x equals -1. Okay, so to wrap up today, let's do a few exercises. Let's focus on these first two. Try to knock these two out in about 5 minutes or so. And if you get to the third one, kudos, but don't worry about it if you don't get to the third one. We'll focus on the first two in 5 minutes or so. Okay, we're just short of 5 minutes, so let's pick up here and wrap up for today. So our first one, x squared plus 8x plus 15 equals 0. We do note that we have a quadratic and we have everything on one side. We have a 0 on the right-hand side, so we are ready to go. We factor this left-hand side. It factors in x plus 5 times x plus 3 equals 0. The product of two things equals 0, so either the first is 0, either x plus 5 is 0, or the second, x plus 3 is 0. And we solve x plus 5 equals 0, x equals -5. We solve x plus 3 equals 0, x equals -3. These are our two solutions, -5 or -3. As a little bit of an aside, you might be noticing a pattern that, when we factor, at least for these simple problems, we kind of end up with a 5 and a 3 here, and we end up with 5 and 3 in our answer. And you might be tempted to do something like skip a couple of steps, and when you do your factorization with your m and n, just kind of pop something like m and n is the solutions. I'd be pretty cautious about doing that. I would recommend not doing that I would recommend going through all these steps. And the reason is that notice that your like m and n would be +3 and +5, but your answers are -3 and -5. So, right, the m and n don't correspond directly to answers. They're kind of off by a negative, and anytime that something's off by a negative, it's really easy to make a mistake if you start taking shortcuts or cutting out steps. So I would recommend going through this whole process. It's only a couple more lines to, I suppose, really only one or maybe two more lines to kind of write out the full process. And it keeps all of the negatives straight. And also when we get into more complicated problems, it's going to work a lot better there as well. So for these simpler problems, you might have noticed that pattern. And if you did, good. A lot of math is about pattern recognition, but that might be a pattern that we want to avoid using to take a shortcut just because of number one, it doesn't generalize too great to future problems that are a little more challenging, and number two, it's easy to drop a negative sign and make a mistake like that when you're cutting out a couple of intermediate steps. For this next one, we notice that the right-hand side is not 0. So we push everything onto the left-hand side by adding 18 to both sides. So I get x squared plus 11x plus 18 equals 0. That factors into x plus 9 times x plus 2 equals 0. So either x plus 9 equals 0 or x plus 2 equals 0. Either x equals -9 or x equals -2. Those are my two solutions. And then lastly, if you got to the third problem, great. If you didn't, don't worry about it. Depending on how long it took you to factor these first two, that's going to depend on whether you got to the third one or not. But the third one, again, we see something non-zero on the right-hand side. We add 19y to both sides to get y squared plus 19y plus 60 equals 0. That factors to y plus 15 times y plus 4 equals 0. And we get our solutions y equals -15 or y equals -4. Okay, so that wraps us up for today. As I mentioned earlier, we have spring break this coming week, so enjoy the time off. Take some time to rest and relax. But like I said, I strongly recommend against just not touching the material for basically a week and a half until next Tuesday. It is a lot to expect to get that momentum back up and running in a couple of weeks and turn around for finals week. So maybe touch base with some of these factoring problems, do a little bit of factoring practice. Like I said, maybe like Tuesday and Saturday, something like that, or like Wednesday and Friday, whatever works for you. But do some factoring practice, do a little bit of practice with these solving quadratic equations. When we come back, we will continue with solving quadratic equations. And yeah, then it'll be a pretty quick turnaround until the end of the class, and summer is on its way pretty quickly here. So let me stop the recording.